So, imagine you are walking in the street minding your own business and happen to run into an old friend. So, you are both catching up, but he's talking like this. He's saying, I was in the park yesterday. I met John in the park. John was walking his dog. John adopted his dog last week. Then I met Mary, and I told Mary that I have just met John in the park, and that John adopted a dog last week. You see, he kept mentioning John's name a lot. We don't do that, right? That's redundant. Usually you would mention someone or something once and then refer to the thing or the person using words like he or she or this or that. So instead of saying John every time, he could have just said he. And the second time he mentioned Mary, he could have just said she. Because we already got it. And we know what we are talking about, right? And instead of telling a story twice, he could have just said, I told her that. Because we don't need to be redundant. We don't need to say things all over again and again. And that's something we do naturally when we talk. And that is some sort of a compression. You see, we do the same with computers too. We try to avoid redundancy. To give you an example, consider the following array of bytes. We have this array of bytes, 862, blah blah blah. If you look closely, you will see that 624 has been mentioned 3 times. Here, here, and here. So instead of mentioning 3 times, we can just mention it once and refer to it later. How? Let's create a list of all the words that has been repeated, which we can call patterns. So here's a list of all the things that has been repeated. Under 0 we have got 6, 2, and 4. And we can substitute here, instead of 6, 2, 4, again and again we can just refer to the item number 0 in the list. So under the index of 1 we have got 3 and 5, and we can also substitute it. Do we see any other patterns? Well, we also see another pattern. We have the index 0, which is 6, 2, 4, is also a part of a bigger pattern sometimes, which is 6, 2, 4, 9, or the index 0 and 9. So we can simply add this to the list too. Under the index of 0, it's substituted with the index of 0, under the index of 2, we substitute it with 0 and 9. Okay, do we still see any other patterns? Maybe not. Okay, let's just say that this is the compressed output. So the compressed output would be the list and this compressed string. So of course you'll need the list to decode that. One more thing that I pretended not to notice until now, which is in a binary form, how do we distinguish between the indices and data? So for example, how do we know if that 0 is a data that meant to be 0 or an index referencing to something in the list? We can think of many ways to do so. One of them is actually not to start from 0. Let's start from 10, because I see that the maximum here in the data is 9. So we'll have to mention that the maximum is 9 and anything bigger than 9 is an index. So in this case, it will look like this. We have the list. Instead of 0, we'll say 10, referring to 6, 2, 4, 11, referring to 3 and 5, and 12, referring to 10 and 9. And of course, we have to mention the list. We have to mention the maximum, our range. So in this case, our range would be from 0 to 9 is data. Anything bigger than 9 is an index. Okay, so that is some sort of a compression. Now, before we talk about a real compression algorithm, I'm gonna state something that is pretty much obvious, but I think it still needs to be said. We need to pack our bits. We should not approximate them to bytes. So if we have something that is only occupying 4 bits or 9 bits or 8 or 10 bits, we will just have to pack everything together. So we are going to be using some bitwise operations. So instead of occupying an entire byte, we can just fit 2, or maybe we can fit 1.5. The rest will go to the next byte. I mean, it all depends on your size. but we'll have to use some bitwise operations like shifting and ORing and masking and all of this so we can fit them together without wasting bits. So from now on, just assume that everything is packed and everything is read with bitwise operations. Let's go back a second to our first example. So you met your friend and you're catching up. Now you want to be less redundant. So, do we start with a list of things that you are going to use many times in your small talk? Are you going to say, "Hey friend, before we talk, let me give you this list. So when I say he, I mean John. And when I say she, I mean Mary." No, we don't do that. That will still be weird, okay? So you're going to be talking normally, naturally. And the more you talk, the more context you are building up in your head, gradually. So you will mention John normally at first, and then once you mention him again, once you mention him the first time, you will build a dictionary in your head. Oh, we are talking about John. The next time you say he's referring to John. This dictionary is only in your head. It's being built through the whole chit-chat. It's not going to be given to you before we talk. So our algorithm in this video is going to be kind of the same. It's called the LZW algorithm. And I can say that it's kind of a lazy, quick algorithm. It's not going through the whole text over and over again to find patterns. No, it will just go through it once and only once. And then we compress it as we go. And it never looks back. So basically, it's doing the same as we do naturally. We just mention something once, and the next time we mention it, we just refer to it with an index. Okay, let's just start with an example. So in this example, the maximum here is 15, so we can have indices starting from 16, okay? So anything between 0 and 15 is going to be data. Anything starting from 16 and up is going to be an index. Okay, so this is the raw information, uncompressed. So we start from 3. Have we seen anything starting with 3 in the dictionary? Oh, what dictionary? We just started right now. The dictionary is still empty. Okay, let's insert 3 into the output stream and let's see if there are any other patterns to insert. So we have 3 and 5. Now the question is, do you think we should add 3, 5 to the dictionary? I mean, in case we see it later, in case it got repeated. Do you think it will be a pattern? Well, I don't know. I haven't seen the future yet. And we said before that we are going through the text only one time. We never look back. So we don't know that's going to be a pattern or not. So in this case, we're just going to keep it in the dictionary just in case. We don't know if 3, 5 is going to be repeated, but in case it is, it has an index in our dictionary. So under the entry of 16, under the index 16, we have 3 and 5. Okay, moving on to the next. Now we have 5. Have we seen any patterns starting with 5? No. So we insert 5 into the output, and we always, every single time, we have to make an entry to the dictionary. So with our next letter, we have 5 and 4. Should we insert it just in case? Should we insert 5 and 4 just in case it's a pattern? Well, the answer is always yes. So we insert our entry to the dictionary. So under the index 17, we have got 5 and 4. Okay, the next is 4. Have we seen any pattern starting with 4 in the dictionary? No. Okay, so we output 4 to the stream, and we have 4 and 14 under the index of 18 in the dictionary. The next is 14, and we do the same. And along with 11, we enter 4 and 11 under 19. Then the next would be 11. We do the same. And along with 5, we have 11, 5 under the index of 20. Then we have got 5. And wait, I have seen a 5 before in the dictionary. We have a pattern starting with a 5. Yes. So its second letter also is matching our second letter. So that's a pattern. So yeah, we have 5 and 4, and we have an index that is already in the dictionary under 17. So in this case, we will not insert 5 in the output stream, but we will just insert 17. So here the pattern 17 has proven itself worthy. I mean, we are just inserting patterns all the way as we go, but nothing has been repeated before. But 17 has actually made it. So instead of considering 2-letter patterns, we might as well consider 3-letter patterns. And in this case, let's check the next letter. It's 9. So in this case, 17-9, or as we can say 549, could also be a pattern. So we're going to be inserting this under 21. And next we have got 9. And we'll do the same thing. We haven't seen any pattern starting with 9, so we'll output 9 in the stream, and we can insert 911 as a new pattern of index 22. The same goes for 1112 under 23, 1214 under 24, and we find another match. We have seen patterns starting with 14 before. Does it also match our next letter? Yes, it's 1411 as well. So we'll insert 19 in the output and make a pattern of 141115, or we can also say 1915 under 25. And then we'll have 15.5. Never seen anything starting with 15 before, so we'll just add 15.5 under 26 and 15 in the output. And then we have got 5. So the question is, do we have patterns starting with 5? Yes. Actually, we do have 2 entries in the dictionary starting with 5. Okay, let's just take the longer one. The longer one also matches our next. So we have a pattern of length 3 under 21. So we'll insert it along with the letter next to that pattern, which is 11. So under 27, we have an entry of 5, 4, 9, 11. Okay, I think we are about to finish. And notice this is really important and really tricky. We have several patterns starting with 11, but none of them are 11, 11. So we'll just insert 11 in the output stream, and every single time we have to insert a dictionary entry. So we have got 11, 11 under 28. Seems normal, right? Now we start from the next 11, the next letter. And do we have any patterns starting with 11? Actually, yes, there is a match with one that we just entered right now. It's 28 representing 11, 11. And in this case, we are done. Okay. Now, can we decompress this output and see if we can get the original again? Let's do it. Okay, so of course, we don't start with just no information at all. The only information we have is that we have a range from 0 to 15. So anything from 0 to 15 is data that is uncompressed, and anything higher than 15, it's a pattern. Okay. So since we are going from 0 to 15, this means we use 4 bits, but actually since we have indices that are higher than 15, we'll start with 5 bits, right? So because it could be 16, so we need 5 bits instead of 4 bits. I mean, the original data had 4 bits, but the compressed will have 5 bits per letter. Sounds wasteful, doesn't it? So at the cost of removing repetitions, we are actually increasing the length of each letter. Okay, let's get going. First, we have a 3, and 3 is data because it's between 0 and 15. It's not an index. We will just have to put it in the output stream, which is the original uncompressed data. Okay, so output 3, and the next is 5. Oh, that's also data. Let's put 5 to the output stream. But first, let's recreate the dictionary. So we combine the previous pattern plus the first unit, or the first letter of the current pattern. So in this case, 3, 5 goes to the dictionary under 16. And now we have got 4, and that is still uncompressed data. So we have to put an entry to the table. In this case, 4. I mean the previous pattern, which is 5, plus the first character of the current pattern, which is 54, and we enter it to the dictionary under 17. And then the next is 14. So it goes to the output as well. And we have an entry to the dictionary, which is the previous pattern plus the first letter in this pattern, which is 14. And we put it in the dictionary under 18. You see, we are constructing the very same dictionary. Okay, let's continue. So the same for 11. We have 11 is added under 19. And then we get to 17. And since we know that our range is from 0 to 15, 17 seems to be an index. Okay, we go to the dictionary. We do have an entry that's actually under 17. So we'll output this entire pattern, which is 54. And now we need to add something to the dictionary, right? What would it be in this case? Like we said, it's the previous pattern, which was 11, and the first letter of the current pattern. The first letter of the current pattern. The current pattern is 54. We only pick the 5. The previous pattern was 11, so in this case it's 11. It's 11 5. In this case, this 11 5 goes under 20. And now we have the 9. Okay, that's not an index, that is uncompressed data. So we insert it as it is, and then we have also to insert something in the dictionary, which is the previous pattern, which is under the index 17, which is 54, plus the first letter of the current, which is 9. So we have a pattern of 459 under 21. Okay, we are really reconstructing the same dictionary, and we keep going. So 11 goes as 11, and we enter 9, 11 under 22, and the same for 12, and 11, 12 goes under 23 in the table, and then we get to the next letter, which is 19. That's an index. Do we have it in the dictionary? Yes. We substitute it with 14, 11, and we enter what? Okay, what entry goes in the dictionary in this case? Okay, it's the previous pattern, which is 11, and the first letter of the current pattern, which is 14, and so 12, 14 goes under 24. And then we have 15. That is uncompressed data. So we put it as it is in the output stream. And then what entry we put in the dictionary? Well, it's the previous pattern, which is 14, 11, and the first letter of the current, which is 15. So in this case, 14, 11, and 15 will go in the dictionary. Next is 21, which is an index referring to 17, 9, which is broken down again into 5, 4, 9. And the next letter would be 28. And really pay attention to this one. Do we have a 28 in our table? Actually, no. And that means one thing. It means that the previous pattern should be duplicated. Okay, what? Where did this come from? You want to know how this happened? How did we reach at a certain point where we have an index that's not in our table? In this case, well, you have to rewind the video and check how did we compress the last 11, 11. But for now, I will just give you the final answer. Whenever there's an entry that's exactly equal to the last index in the dictionary, plus 1. I mean, if it's the last index plus 1, that means duplication. It means you should put the previous pattern plus the first letter of the previous pattern. So the previous is 11, so the pattern is 11, 11. And we are done. Okay, one thing you might have noticed is that the index size is increasing. So in the last example, it went from 16 to 28. And if we kept going, it would have kept going too until it's 32 or bigger. And at that value, we'll need to start using 6 bits instead of 5 bits. So what do? Should we have started with 6 bits in the first place? No. We said from the beginning, we will never look back. We'll just go through the data one time. So how do we know if you are going to use 5 bits or 6 bits or maybe 7 or 8? Well, in this case, at first we'll start using 5 bits per letter, and then we upgrade to 6 bits. And the longer the input stream gets, the bigger length of each index gets. You might ask also, okay, so what if the index gets really ridiculously big? Like, what if the index kept going maybe beyond 32 bits or something? What do we do in this case? We have a very lengthy stream and we actually want to compress it, but at the expense of having a ridiculous long length. Well, in this case, I agree with you. It's nonsense to actually use 32 bits when we actually could have used 4 bits from the beginning. You see, I mean, we are using 32 bits for the data that was originally 4 bits, and we are calling it compression. So in this case, we might also put a limit to the index size. So if the index keeps growing and it keeps growing until, for example, let's give it an arbitrary value. Let's say if it kept growing until 12 bits, well, in this case, we have to stop. We have to say, okay, that's enough. We stop growing like that and we start from the beginning. And so in this case, if we are compressing and the index grows beyond 12 bits, we just stop and reset the table and start again from the very beginning. So in this case, we reset. Also, if you are decoding, if you are decompressing, if your dictionary, which is going to be the same dictionary as the other dictionary during compression, if you reach 12 bits, you will have to stop and reset and lose all the patterns, lose everything from the last dictionary that you have constructed and start over again. I'm not saying it's the best algorithm ever, it's just how it is. It's a quick one. Okay, so of course, as we have seen, since both the encoder and decoder are constructing and reconstructing the same dictionary, the decoder should know exactly when will the dictionary become full, which is when the last index reaches 4095. But still, the encoder has to drop a hint to reset the dictionary. So we need like a code, an index that when you see, it means please reset the dictionary right now and start over again. So we have to agree on a code, on an index, on something that when you see in the output stream, it's a command for the decoder or for the decompressor to stop and reset the table and start over again from the initial size, which was 4 bits or 5 bits in our case. And this index is neither like an index in the table nor a data. It's some arbitrary number that we should not use for data and we should not use as an index. So, let's give it an arbitrary number. We said our data is from 0 to 15. So in this case, we will not use 16. Let's use 16 as a reset code. So we start from 17. So the first index will be 17, right? Well, we are going to use another code for ending the compression. So if you see this code, it means we have finished this compression, the stream has ended. Please, go do something else. Make other sense of the rest of the data. It does not belong to the same stream. So we will need a stop code, like an ending code, and a reset code. Reset for the dictionary in case it gets ridiculously huge. So we'll assign 16 in our case as reset code and 17 as ending code. And then we start encoding from 18. Not from 16 as we did in the last example. So actually not exactly 16 and 17, it depends on your size. So if you are using 8 bits data, then you start with 9 bits and then we'll use 256 as reset and 257 as end. If you're having 4 bits data, you'll use 16 and 17 and so on. It could be 32 and 33, it could be 64 and 65. It depends on your length, on your initial length. Okay, so that's how the algorithm works. That's the LZW algorithm. Maybe you have gotten some ideas about compression. Maybe you can take a look at other algorithms and get more ideas. Don't forget to like and subscribe, and I will see you next time.